and it's my very great pleasure to introduce Professor Ed Grew from the University of Maine, who is the 2015 recipient of that award. And I'll be able to say a little bit more about Ed's career in a few minutes when we actually present the awards. But before we do that, we've asked Ed to give a talk now to finish the conference, which is on a topic a little bit different from most of the topics that we've been hearing about here, but I think a very nice and different piece of science to finish off the conference this week. So Ed, very welcome.
Thank you very much for the very nice introduction. My talk today will concern the roles of chance and necessity in the diversification of minerals. Is the Earth's continental crust unique? This is a question that concerns mineral evolution, namely the study of changes in Earth mineralogy over geologic time. This idea was first proposed by A.G. Jabin in 1979, but my co-author, Bob Hazen, has taken it much further, starting in 2008. And more recently, he's introduced the study of mineral ecology, which is the study of processes influencing the distribution, diversity, complexity, and abundance of minerals. This slide shows what mineral evolution is not. For biological evolution does provide some insights into mineral evolution. For example, mineral evolution over geologic time has involved the interplay of stochastic and deterministic processes, or we might say chance and necessity. Another idea from biological evolution is if we imagine a replay of Earth's history, what would its mineralogy be? The famous evolutionist Stephen Jay Gould wrote in 1989 that, quote, "I call this experiment replaying life's tape. You press the rewind button, making sure you thoroughly erase everything that actually happened, and then let the tape run again and see if the repetition looks at all like the original." So in my talk today, I'll first introduce why we think that stochastic processes could play a role in mineral evolution, because one would think that minerals were pretty much determined. And then I'll consider an example of phase relationships in evaporitic borates, whether there's a role for chance. And then another example is the relationship between mineral diversity and element abundance. I'll make a comparison of the Earth with the Moon, and then consider mineral frequency distribution, which is a statistical treatment, and then come back to the idea of replaying the tape of Earth's mineral history. This all began with the paper that I wrote with Bob Hazen, Beryllium Mineral Evolution. At the time we wrote the original draft of this manuscript, we did not consider the role of chance in mineral evolution. I draw your attention to the two plots. The one above is cumulative beryllium mineral diversity. The one on the bottom is what is thought to be the actual diversity at a given geologic time. There are four spikes of diversity. For example, the one for the Elamausic alkalic complex in Greenland that's 1160 million years old. All was fine and good, except that one reviewer of our manuscript challenged the assumption that mineral evolution was deterministic. And this was Gregor Markle. In reference to the Illumausic complex at 1160, he asked, was it at this time, he challenged us, said it was not for underlying reasons that Illumausic was intruded at 1160 million years, but just by good luck. It could have been 1,000 million years later, or earlier, or not at all. And this is what got us thinking on these issues. So here are some brief definitions of stochastic and deterministic processes. Stochastic is the outcome is not determined by the prior history or state. It involves randomness and is not predictable. In contrast, deterministic means there's no randomness involved, and the necessary consequences are given by the antecedent state. It is predictable. With more information, a process previously considered stochastic could become predictable, and thus these are really endpoints, and most processes involve a certain bit of both determinism and stochastic. Well, here's an example of the phase relations in the system sodium borate or sodium tetraborate water. There are three naturally occurring borates in the system: tincalconite, the familiar borax, and kernite. But tincalconite has been shown by experiments to be metastable, as shown in this plot. However, at Searles Lake in California, nice crystals, one of which is shown here, have been found, suggesting it was deposited directly from the brine. It has not been possible to explain this occurrence yet, so we can ask whether the borax, kernite, tincalconite relationships still be considered deterministic, or are we dealing with some element of chance? The next example is the relationship between mineral diversity for a given element versus abundance of that element in the Earth's crust. For example, if you look at the point illustrated for tellurium, that means that indicates the number of tellurium minerals found in the Earth's crust versus the abundance of tellurium in the crust. We see that most points form a distinct trend with a slope of 0.2, but we do have conspicuous outliers. If this were a deterministic process, we need to explain these outliers. So we'll look at the so-called underperforming elements. That is, there are fewer minerals from these elements than predicted by its abundance. Take gallium and rubidium and the rare earth elements. The gallium and rubidium mimic common elements, aluminum and potassium. That means that common minerals like K feldspar and muscovite contain trace amounts of these elements, whereas the rubidium and, for example, the rubidium analog is extremely rare. So it's no surprise that we see fewer gallium and rubidium minerals than predicted. The same is true for most rare earth elements. Only cerium and yttrium often form their own minerals. The other rare earth elements do not. We'll now take a look at the so-called overperforming elements. For example, copper has more minerals than predicted by its abundance. And one reason for this is that copper has multiple oxidation states. Copper also is found as oxides and sulfides. Other overperforming elements like uranium form special ions such as Orono. So now we can explain these outliers, leaving the trend quite clear. However, it would be nice to see whether we could get such a trend from another planetary body. That would be an even better test. And the moon is one possible planet or moon for comparison. We have samples, we have bulk geochemistry, and I compiled a list of minerals for the moon, which I vetted with feedback from lunar specialists. And here we got the trend with a slope comparable to the 0.2 to the Earth's trend, even though we have 2 orders of magnitude fewer minerals on the moon. Indeed, the trend is tighter as there are no outliers. Now, mineral formation on the moon, there are 3 processes that have been documented: igneous differentiation, shock metamorphism, and solar wind. And my apologies, there are no clays on the moon. These 3 listed processes could be giving the minimum diversity for a planetary body. Nonetheless, the relationship between bulk chemistry and mineral diversity holds, consistent with it being deterministic. Now let's turn to the question that how relating the number of minerals to the number of localities where they are found can give us insight on the number of mineral species remaining to be discovered. Dr. Greta Heisted, a mathematician at the University of Arizona, did the statistical treatment on the known 4,937 species and at 450,000 localities. But the key figure is the 650,000 unique combinations of mineral species and locality. She found that the probability that a given mineral is found at a certain number of localities is given by this distribution function, and the observed frequencies agree closely with the prediction by what is called the large number of rare events distribution model, which is based on that function. The key observation in this plot is that 1,000 minerals, that is more than any other, are found at just a single locality. Another way of looking at the previous plots the probability of minerals occurring at a certain number of localities versus the number of localities. And we see that if you chose a mineral from a list of the nearly 5,000 found so far, it is most likely to be reported from one locality. So let's choose 5 minerals, 3 of which are found at a large number of localities, for example, antophyllite, schorl, and calcite. These are representative of the minerals that make up the bulk of the Earth's crust and occur at hundreds, thousands, and even 10,000 localities. However, it's the minerals I've chosen 2 that are found at only 1 or 2 or 3 localities. These minerals constitute the diversity of Earth's minerals and can be considered its mineralogical signature. From the model we saw before, we can follow how many species are found, or we can calculate how many species are found for a number of mineral locality pairs. To date, we've looked at 650,000, that is, humankind has looked at 650,000 mineral locality pairs, and we've discovered over 4,900 minerals. If we looked at many more pairs, we predict that nearly 6,500 minerals could be found. That is, there are 1,500 minerals remain to be discovered. Now, if we replayed the discovery tape, that is, we go back to having no mineral localities known, and we again examined 650,000 number of mineral locality pairs and got 4937 species again, 14% of these species would be different. So how many species could there be, would be plausible on a replayed Earth or Earth-like planets? We make some fairly rough assumptions, such as that each of the 72 elements forming Earth's crustal minerals has the potential to produce 1,000 species if sufficiently concentrated, such as oxygen, silicon, aluminum. If the average Earth mineral formula has 4.7 different chemical elements, then a rough estimate is that there are over 15,000 plausible species that could occur on a replay of Earth or Earth-like planet. Let's do 3 thought experiments. First, we replay of the tape of mineral discovery, which we already examined. If we assume the same total species and localities, then 14% of the first 4937 discovered minerals would be different. A second level is if we replay Earth's mineral evolution itself. We start with the same bulk composition, add the plausible minerals. Bulk chemistry can be a deterministic factor for mineral diversity, the slope of 0.2 we saw earlier. Stochastic features include bulk chemistry of the Earth's crust, crustal properties, processes, mineral evolution, biological evolution. The third thought experiment, or third level, is mineral evolution on another Earth-like planet. Here we'd have a different starting bulk composition, but we'd be adding plausible minerals as before. We have an additional stochastic factor that's so-called planetary stoichiometry. Thus, in conclusion, given the number of plausible minerals and the characteristic, quote, large number of rare minerals distribution on Earth, the planet's mineralogy is calculated to be essentially unique. This uniqueness would not be possible if mineral evolution were deterministic. Stochastic processes contribute to the potential for irreproducible diversity. Thank you.
Thank you again, Ed, for a very thought-provoking talk that I think has got us all thinking about minerals in a rather different way at the end of the afternoon here. Thank you very much indeed.
Well, thank you.